Okay, why don't we get started? Thank you all for coming. So today we're going to hear from Magda. She'll be giving the public talk as part of her thesis defense. So Magda, as probably most of you know, is originally from Germany. However, none of her higher education was actually completed there. She got her undergraduate degree at the University of Glasgow, and at the same time she got a master's degree there, partly working with Ramesh in some of her research. So as an undergraduate, she worked on pulsars and also AGN outflows driven by active galactic nuclei. Once she came here, she became interested in binary star systems, and in particular binary star systems that are surrounded by disks of gas that interact with the binary and affect its dynamical evolution. So she's combined a series of numerical simulations with physical insight to obtain a lot of new and interesting results and resolve some confusion in the literature over some of the previous calculations that were similar to hers. Her results are broadly applicable to any binary star system, say ordinary binary stars, possibly also to the formation of extrasolar planets around binary stars. And so these are things that she hopes to pursue as a postdoc. But her thesis research was mostly about binary systems of supermassive black holes, so black holes that have masses millions or billions of times the mass of the sun. So she studied the interaction of these binary supermassive black holes with surrounding disks to understand their dynamical evolution. And this is very important because once the black holes come close enough together, they can coalesce and they would be strong emitters of gravitational radiation at that point. So her work has direct connection with recent detection of the gravitational wave background, and partly as a consequence of her research, she's been invited to join the NanoGrav collaboration, which is exploring the gravitational wave background, which is mostly contributed by mergers of supermassive black holes. So in addition to her research here, she's been very active in engaging the community at the CFA and also the surrounding neighborhood. So she'll talk about this later today, but she founded the CFA garden outside of A building. That's been a major source of engagement for people here, not just here, but also in the surrounding neighborhoods. Magda's been very productive as a student here. She's co-authored 29 papers already, and partly as a consequence of the significance of her work, she was offered many positions last year when she applied for postdocs. And in the end, she decided to take a prestigious Simons Fellowship given by the Simons Foundation in New York, and she'll be starting at Columbia in a few months. So take it away, Magda.
Thank you, Lars. Can you all hear me good? Yeah, great. It's wonderful to see so many of you here and hopefully online. Welcome, everyone. So today I'm delighted to tell you about some of the highlights in my thesis work, which is titled Signatures of Circumbinary Disk Dynamics in Massive Black Hole Binary Populations. And I really hope that by the end of this talk, you'll have a deep understanding of circumbinary disks and what they are, and how they dynamically affect binary evolution on a variety of scales. Okay, so I will start, obviously, with the science. I will talk about circumbinary disks and massive black hole binary systems. And then I will also talk about extracurriculars, and Lars already gave it away. That's the garden. And I will finish with a very brief section of acknowledgements. Okay, so the science section is divided into two parts. I've chosen to first tell you about theory and simulations, including basics about binaries, so binaries 101. Then I will talk about circumbinary disks, what they are and why they are interesting. And then I will present maybe the first comprehensive binary evolution model in circumbinary disks. I will then move on to predictions for astronomy. So basically, how does this theory relate to real astrophysical sources? And I will talk about massive black hole binary systems, how they form, and how we may observe them. And I will talk about the gravitational wave background, which is emitted by these massive black hole binary systems. And strong evidence for this background was found and published on June 29th of last year. So we have a lot to cover. Let's get started. Binaries 101. So why are binaries interesting? The relevance of binaries in astrophysics, I don't think it can be overstated. There are so many different types of binary systems. We know that binary stars form mostly in binaries. We also know that there is a lot of historical significance to binary pulsar systems. In 2015, the Nobel Prize was awarded for the first detection of gravitational waves from compact object mergers. There's a long-standing history of studying X-ray binary systems, and of course, relevant to this thesis, binary supermassive black holes. And I've added some, question marks here because there might be many binary systems we haven't discovered or I might not have mentioned here. Okay. So what is a binary system? It is essentially two bodies orbiting their common center of mass and two gravitationally bound bodies. And just to give away the lingo that we're going to use here, M1 in green is the primary or heavier part of the binary system, and M2 is the secondary or lower mass part of the binary system. And if I let this simulation evolve here, you can see how this binary system would move on its orbital path. Okay. Now we can talk about parameters that we use to characterize binary systems. So we define the mass ratio of the binary system as the secondary over the primary mass. And since the secondary is always lower mass than the primary, that is always less than 1. And this is just a convention. I'm mentioning this because other fields use exactly the opposite, and that can get really confusing. Okay, then there's the semi-major axis, which for our purposes we'll use as a proxy for the separation of the two bodies in the binary system. And finally, the eccentricity EB, which measures sort of the flattening of the orbit. So you can have a perfectly circular orbit, or you can have something that is slightly flattened along some axis, and that is characterized by the eccentricity. Okay, so having covered those parameters, I want to give you a bit of an intuition for what these different orbits would look like if I explore this parameter space. So here we're looking at a grid of mass ratio versus eccentricity, and you'll see a lot of that, where we look at binaries with mass ratios from 0.1 to 1, and eccentricities from 0, which is a circular orbit, to 0.8, which is a highly eccentric orbit. So for a circular orbit for a circular binary with a low mass ratio, you can see that most of the mass is in the primary, and the primary is very close to the center of mass. Now, if we increase the mass ratio a little bit, you can see that both of the bodies move a bit closer together, and they're at a more similar distance from the center of mass. And finally, for an equal mass ratio binary, the system is entirely symmetric, and the bodies are essentially indistinguishable. Okay, now let's increase the eccentricity. Now we're looking at an eccentricity of 0.4, and that means that the orbit is somewhat flattened. We no longer have a circular path on which the binary moves. And we can then increase that eccentricity. I don't know if you can see this. I'm going to move out of the way. You can increase that eccentricity to extreme values, where you can see that flattening of the orbit more so than before. And of course, there's a parameter space in between, where the binary is neither equal mass nor circular. So it's about exploring this entire regime. Now, next I want to talk about what are circumbinary disks. So circumbinary disks are essentially accretion disks that orbit a binary system. And for that to make sense, I'm first going to talk very briefly about what accretion disks are. So accretion disks are flattened disks of gas and dust that orbit a central body. So you can see here that red arrow indicates the rotation of the disk, and then there are these microphysical processes in the disk that actually cause dissipation of angular momentum outward. And that leads to the disk moving inward towards the central body. And this process facilitates the process of accretion, which is really, really important in astrophysics because it allows us to observe many systems. Okay. So this looks fairly symmetric. However, if we have a binary system at the center of an accretion disk, the situation is a bit different. Instead of the disk moving all the way inward due to the viscous drift inward, which is facilitated by these microphysical processes that I talked about, the binary actually exerts gravitational torques on the gas. And these gravitational torques stop the gas from moving all the way inward, and that creates a cavity or a hole in the center of the disk. And as a result, the disk is much more asymmetric, and a lot of much more complicated nonlinear physics and dynamics will take place. And exploring that and exploring how that affects the binary evolution is the goal of the simulations that I'm about to show you. Okay, so we'll talk about binary evolution in circumbinary disks now. So in order to determine how this asymmetric morphology of the circumbinary disk affects the orbital evolution of the binary system, I ran a very large simulation suite of binaries immersed in circumbinary disks. So I know this is mesmerizing, but let's unpack what we're looking at here. So here on the vertical axis, we're looking at binaries with different mass ratios. So we're starting at a mass ratio of 0.1, going all the way up to 1. So remember, this is what I showed you earlier. There's a mass ratio and an eccentricity in the system, and it tells you about what the orbit of the system looks like. On the horizontal axis, we're looking at increasing eccentricities. So from circular, eccentricity 0, all the way up to the value of 0.8 that I showcased earlier. And all of these disks, all of these binaries are immersed in the same initial disk configuration. And the goal is then to figure out what the gravitational interaction between the disk and the binary produces at the end over long periods of time. So the colors here indicate surface density, and the light green or yellowish color indicates very high densities, whereas the dark purple indicates a very low density region. And here you can see what I pointed out earlier, that the binary sort of stops the gas from moving inward and creates a cavity in the center of the simulation. But you can see that accretion, or the process of the binary feeding of the gas, is not entirely stopped. For instance, here you can see these streams leading from the disk to the binary system, right? You can see there are streams that feed the components of the binary. So the binary is still growing in mass and accreting. It's just doing it in a much more complicated way. And while it's not entirely certain how this accretion takes place, despite the gravitational torques that cause the disk to sort of remain at a distance from the binary, it's likely that it's something to do with a certain unstable points in the gravitational potential of the binary that allow perturbations to leak gas into the center of the domain. Okay. So this was incredibly expensive to run. Why do we do it, right? Why do we do all of this? We do this because we want to understand how binary systems evolve in circumbinary disks. And what we want to understand in particular is how does the mass ratio of the binary system evolve? So how is the accretion rate divided by the primary and the secondary? How is the semi-major axis, or the separation of the binary, evolving because it's interacting gravitationally with the gas that surrounds it? And finally, and that's my favorite, how is the eccentricity of the binary system evolving due to what we now know, resonances in the disk and gravitational interaction with the gas in the disk? So the results were divided into 2 papers, but I think we can sum them up in 3 points. So we found that the mass ratio of the system always increases when a binary is immersed in a circumbinary disk. And what that means is that the primary and the secondary mass essentially move towards the same value. So eventually, we always end up with a mass ratio equal to 1. Okay. So secondly, we find that the binary separation can either shrink, as shown here, or it can grow, as shown in the next movie. And which happens depends on the mass ratio and the eccentricity of the system. So all of these parameters are linked with one another. Finally, we found a really exciting result, similar to what Paul has found in previous work, that there's a steady state eccentricity induced by the circumbinary disk. So what that means is even if you start with a binary that is on a nearly circular orbit, the eccentricity of the binary system will increase as a result of interaction with the disk. And so this fun movie that I'm showing here shows you an initially circular orbit that then widens into a more eccentric orbit. And it doesn't keep doing so indefinitely. the binary finds an equilibrium eccentricity at which it wants to live, and the disk keeps the binary at that eccentricity. Okay, great. So let's look at this model in one plot. And in order to do so, I've run a sort of population synthesis study of binaries that are populating the mass ratio versus eccentricity space here. So what I've done is basically just sample randomly the eccentricity and the mass ratio of, I think these are a couple thousand binary systems. And then I apply the evolution rates of the mass ratio, the eccentricity, and the semi-major axis to these binary systems and show you what happens. So the binaries are here. Then we can overplot for each part of the parameter space the evolution of the semi-major axis. So remember, the semi-major axis is the separation of the two components of the binary. And in this color bar here, the blue region, which is taking up most of the space, indicates that at that part of the parameter space, for instance here, binaries want to inspiral or shrink their separation. Whereas the red part of the parameter space, which is most prominent here, indicates that the binary wants to expand or outspiral. And so we can tell from this map whether binaries in this parameter space want to shrink or expand. So that's already good, but we can do more. We can add these streamlines which tell us about the evolution rate of the eccentricity and the mass ratio. So you can see how the streamlines here all point to your right, and that is indicative of the result we found about the mass ratio, that the mass ratio of the system always increases. Going to the right means a higher mass ratio. However, we found that these arrows can either point down or up, which means that the eccentricity can either decrease or increase. And if we then run a full simulation of the system, we can see that the binary systems move along these streamlines and populate the center of this plot. So they populate this kind of straight line that you saw previously, and then remain on this straight line, only moving upwards towards higher mass ratios. And this is significant because we have an initially randomized parameter space that then evolves into a very neat 1D solution. So we have this equilibrium solution for binaries, regardless of what their initial conditions are. This is really significant, right? And it's kind of fun to watch, actually. Okay, so we have this model, and since these simulations are scale-free, we can apply this model to binaries on all sorts of scales. We can say this model can be applied to binary stars forming in disks, right? Because that's a circumbinary disk. We can also hypothesize maybe there is some gas around binary pulsars, who knows? Maybe there's some similar configuration eventually evolving in X-ray binaries as the companion expands and there's a common envelope phase, who knows? We know for sure that binary supermassive black holes experience inflow of gas at regular intervals. And in this part in this example, we can definitely use this model, and this is what I will talk about in the next part of the talk. But here, to summarize, we have found that with a large parameter study of mass ratio and eccentricity, we were able to construct a comprehensive binary evolution model of binaries in circumbinary disks. We found an equilibrium solutions for these binary systems, and the scale freeness allows us to apply this model to binaries on a variety of scales with caveats. Okay, now let's talk about the second aspect of this talk. Let's talk about predictions for astronomy. Does this even matter, right? Is this relevant for binaries if we actually look at physical parameters? Okay, now before I apply the circumbinary disk models to massive black hole binaries, I want to first tell you what these systems are and how they form. So one observation in astronomy that has become very clear in the last few decades is that when we look at galaxies, most galaxies harbor a massive black hole at their center. And this is especially so for the most massive galaxies. And as these galaxies merge, as they do in the a model of hierarchical structure formation that we have, we eventually end up with a remnant galaxy. Now, this remnant galaxy will then contain two massive black holes. What happens next? So what happens next is an area of ongoing research, and numerical simulations have struggled as of yet to really fully understand this, but the framework is that the gravitational background of the galaxy essentially allows the binary system to form at the center of the newly formed galaxy and sort of spiral inwards, so sink to the center of the newly formed remnant galaxy post-merger. What has also been found is that in post-merger galaxies, the gas that was contained in these previous galaxies is funneled in towards the galactic center of the new galaxy. Now, we have this binary system forming at the center, and we have gas inflow. This might remind you of something. This might remind you in this plot, where I've shown you a binary system surrounded by gas that moves towards it. Now, what that tells us is that binary systems, massive black hole binary systems at the center of galaxies will frequently form circumbinary disks, and that is triggered by the gas inflow in a post-merger galaxy. Now, we can then hypothesize that a circumbinary disk will govern the orbital evolution of the binary system for some time. And the question that we want to ask is, can we see signatures of this circumbinary disk dynamics in massive black hole binary populations? And by signatures, I mean something like this, where the binary eccentricity is related to the binary mass ratio. Maybe we can see this. First, however, we have to detect massive black hole binaries at scale. So, and the reason that this is a good time to think about this problem is that the Vera Rubin Observatory will likely get first light in the next year and is expected to detect up to 100 million massive black hole binary systems. And so that is a really, really good sample to start probing the properties of this population and to look for signatures of circumbinary disk dynamics in the massive black hole binary population. But in order to understand whether circumbinary disk dynamics was relevant in the evolution of massive black hole binary populations, we first want to model this theoretically. We first want to understand what is the census of massive black hole binaries in the universe and what happens when we apply our models to this population. And in order to do so, we use cosmological simulations. So this is a video from the Illustrious TNG simulation, where we're really just looking at a really beautiful rendering of the cosmic web. And looking at this, I want to illustrate that in these filaments of the cosmic web, we'll probably get merging galaxies frequently. And so what we can do with these large-scale cosmological simulations is we can probe the formation and evolution of massive black hole binaries at large scales. And by doing so, we can extract their initial conditions, like we can know about the black hole masses, we can know about their separations, the distance to us, and the host galaxy properties in which these binaries form. Now, cosmological models such as this are simply too large volume to resolve the processes that lead to the formation of a small scale massive black hole binary. So we really just extract the properties of the binary. And then we use a code called Holodeck that I'm helping develop as part of the Nanograph collaboration that's led by Luke Kelly, who's hopefully watching. Hi. And we extract the initial conditions of these massive black hole binaries from cosmological simulations, and we come up with a sample of 2,749 binaries with initial conditions such as mass ratio, binary mass ratio, separation, and their redshift or distance to us. So we get some kind of census of the massive black hole binary population that should be out there from cosmological models. Okay, following that, we model this process semi-analytically. We model the process by which massive black holes sink towards the center of the remnant galaxy. And that allows us to then come up with a sample of tight, gravitationally bound massive black hole binaries. And from then on, we can apply our circumbinary disk models that then start applying once the gas is funneled towards the galactic center. So we have a population of 2,749 massive black hole binaries from cosmological simulations, and these are evolved with semi-analytic models. Now, there are many processes in the galaxies that lead to the formation and the shrinking of the binary separation, the eventual merger of the black holes. And we can choose to either exclude circumbinary disks from the equation or include circumbinary disks from the equation. One thing we do not have at all is the initial eccentricity of the binary systems. We have the mass ratios. These are sort of, you can think of them as a consequence of hierarchical structure formation, because the mass ratio of the binary that forms is a consequence of the two galaxies that have merged. Okay. But the initial eccentricities at which the binary forms are highly uncertain, and they will change completely due to small changes in the orbit of the galaxies that initially merged. So it's a very unstable quantity. So what we've done here is we've extracted the binaries from the cosmological simulations. We let them get towards the galactic center. We record their mass ratios. And then we assign them randomized eccentricities because we simply don't have a good model for that. Then we keep the simulation running. And we either exclude circumbinary disk dynamics or we include it. And I will let this run. You'll see the binaries, you'll see the binaries evolving in time. You can see there's not much movement here. But with circumbinary disk dynamics, you see a very quick shift towards the center of the plot, which should be reminiscent in the plot that I showed you earlier in the first part of the talk. Okay. So looking at this, we can then say that if we exclude circumbinary disks from the semi-analytic model that we use to model the population of massive black hole binaries, then our predicted observations of these binary systems are entirely dependent on the initial conditions we assign. Because in this example, the randomized eccentricity distribution stays random. However, if we include circumbinary disk dynamics, then a clear structure emerges that is a signature of circumbinary disk dynamics in the evolution of massive black hole binaries. And so this is what we want to look for when we look for signatures of circumbinary disks in massive black hole binary populations. Okay. So now let's talk about the gravitational wave background. Many of you who are in the field will have heard about this. It's been a very interesting and exciting year for the nanograph collaboration and other pulsar timing array collaborations in the last year. But let's talk about what the gravitational wave background is and how we might see it. So I told you about massive black hole binaries forming as a result of galaxy mergers and then sinking towards the center of their galaxies, forming binary systems, and eventually merging. Now, throughout this process, they're also emitting gravitational waves, sort of like this, and merge and grow. Yeah, I like that one too. So imagine there's a massive black hole binary going off somewhere near Earth. Imagine we had some detector we could use to detect this, the signature of gravitational waves. Now, we could easily tell that this was one single gravitational wave event. Maybe we could even tell there were two distinguishable gravitational wave emitters if there were two binaries emitting at the same time. But now imagine the universe is isotropic and homogeneous. So, so imagine this happens everywhere all at once, right? Then you have a problem because you can't distinguish any of them. But what you also have is what we call the gravitational wave background. You have a constant background hum of gravitational waves that are constantly emitted by massive black hole binaries throughout the cosmos. And we can mathematically describe this background. So here, this is the only formula I'm going to show, so just, bear with me. So H is the strain of the gravitational wave background, or the loudness of the background that is emitted by the massive black hole binary population. And this is dependent on the frequency at which the gravitational waves are emitted, but it is also dependent on the properties of the individual massive black hole binaries that emit the gravitational waves. So in particular, the chirp mass. Now, let's imagine that we have this sample of massive black hole binaries from cosmological simulations. We can plug the properties of these binaries in here, and we can calculate the gravitational wave background. No problem. OK, so here you're seeing, again, the strain, h, and the gravitational wave frequency on the horizontal axis. And it has this nice power law that we know it should have. And we're basically done. But here we haven't used circumbinary disk accretion in the entire evolution of the population. Why should we do that, though? So the reason we should do that is because the background is highly sensitive to a quantity called the chirp mass, which is highlighted in red here. Now, the chirp mass depends on the mass ratio of the binary. And we can therefore say that the strain or the loudness of the gravitational wave background depends on the median cumulative mass ratios of massive black hole binaries in the universe. We have also learned in this talk that circumbinary disk accretion leads to an increase in the mass ratio, which leads to an increase in the chirp mass. And that leads to an increase in the gravitational wave background strain. Great. So that gives us some motivation to include this accretion flow in our models because it might affect the gravitational wave background amplitude with some significance. Now, the significance to which this effect is dominant depends on how much gas is available to the binary system. So let's see what happens if we only allow the binary to accrete a very small amount. So this is shown by the green line here. Here we have allowed the circumbinary accretion disk to supply a small amount of gas to the binary. And we see that even a small amount of gas leads to some shift in the amplitude of the background. Now let's increase that accretion rate and increase it further. And we have, at our maximum accretion rate tested, almost an order of magnitude shift in the gravitational wave background amplitude. And this is not just because the binaries grow in mass, it is also because the binaries grow in mass ratio. So it's not just more massive binaries, it's also a shift in the properties of the population that causes this effect. OK, so that leads me already to a summary of part 2, which is that circumbinary disks likely form in massive black hole binary populations. The equilibrium eccentricity that we've predicted in our circumbinary disk models could leave a signature in the populations of these binaries that we are about to detect with the Vera Rubin Observatory. And finally, the circumbinary disk-driven mass ratio increase boosts the gravitational wave background amplitude. OK, great. So the science part is done. Let's talk about extracurriculars. So the extracurricular activity that took up a lot of my time has been the astronomy garden at the CFA, or we named it ASGARD. It's a fun acronym. We like acronyms, right? So in 2020, when the COVID-19 pandemic forced us all to isolate and be inside, a few of us had this idea that we should use this space, which is not far from here, just behind a building, to build a vegetable garden and find some way to be outside and be together maybe and do something productive. You know, find some kind of community in these really hard times also. So we got together, some of us. We got leaves, all sorts of organic matter. We got these nice, what do you call them? Pallets, yeah. Got these pallets to build beds out of. We got our hands dirty, and it wasn't just me. There were plenty of us. This is Claire, Kuba, Floor, who's now no longer here. But we got our oh, not what I meant. She's in New York. She's what? She's fine. Okay. Floor's well, and she helped a lot with the garden. Okay. We also had Lika and Alexia helping build this herb garden, and we got this huge delivery of soil that we used to build our vegetable beds. This was like a 3-day job. You can see Gus and Lika here really, putting a lot of human power into this. And this was, I think, the second day of that pile. Now, this was, I think, the third day, and by that time we had a good amount of vegetable beds built. And by spring 2021, it looked something like this. We started getting vegetable beds, we started mulching, and things started looking more alive than previously. Great. Okay. But enough is never enough. The gardeners in the room know that it's always about next year. So we started building these vertical trellises, and we built this really nice arched bed. Again, there were several of us helping. You see familiar faces again, getting their hands dirty. And we got our first harvest. So here you see the vertical trellises overgrown with pumpkin and cucumber vines. And we got this really nice pumpkin. This is Mike, Dr. Mike now. And you can see it has a tan line because we actually had to support it with a hammock so it wouldn't fall off the vine. And these tiny little sunflowers too. Yeah. We harvested a lot of produce, and for graduate students living in this part of the country, this was not an insignificant perk. So it was wonderful. We carved some of the pumpkins. We had some fun social events, and we got this one precious watermelon as well. It was great. So there was less glamorous work involved too. Some neighbors of the CFA showed me this great goat manure pile in Belmont. I can tell you all about it. But yeah, we got our hands dirty, and it was wonderful because we were not doing this alone. There were a bunch of people getting together, and the group started getting bigger and bigger. And in 2022, we had this wonderful group of people harvesting together and taking home the produce that we grew here. So that was great. Last year, we did, again, new things. We started mushroom gardening. We inoculated, Lars helped actually, we inoculated the beds with oyster mushroom spawn and wine cap mushrooms. And we harvested a lot of mushrooms, and they should come back this year, so keep an eye out. Now, I'm getting quizzed today, so I decided I'm going to quiz you as well. These are native plants that grow in the astronomy garden, and I'm asking for volunteers who know the names of any of them. Kuba?
The cactus will be prickly pear.
Yes, okay, great. Prickly pear, great. You can only go once, so. Anna Maria?
The milkweed of the pen.
Yeah, the milkweed, great. We have milkweed, good. Yeah?
I think this is Sonnenhut in German, Echinacea.
Yeah,
which
that's
is
it.
a
Yeah,
plant
the Latin name is correct.
Yeah.
This is spotted bee balm.
I haven't
Great.
got it.
Yeah. This is a variety that's native here. We have cutleaf coneflower, and we have the common milkweed. Excellent. Great. So, nice. In a nutshell, it's been wonderful to go from this space to something that looked like this. We don't know what it's going to look like this summer, but we have 2 new resident gardeners who are taking over the garden. So I'm hopeful and looking forward to visiting in the future and see what else is growing. Okay, I'm going to do very few acknowledgements. I'm doing most of them privately, but a few will be said. Since we talked about the garden, I do want to acknowledge that Harvard University is located on the traditional and ancestral land of the Massachusetts. And I've been very lucky to be able to work and live here and even cultivate the land. So I'm also thankful to the Harvard University Native American program for drafting this land acknowledgement. I want to acknowledge Lars, my advisor, who we all know as someone who knows a lot about hydrodynamics, but he also loves animals and travel and wine, and I've been incredibly fortunate to learn from you, Lars, and to be part of this wonderful group. I want to acknowledge my thesis committee. I'm going to acknowledge them even more after today, I think. Come on, Ido. Okay. Okay. And then I also want to acknowledge my mentors, Rainer Weinberger, who's now in Germany. Rainer has been incredibly helpful in helping me build these simulations that I've shown you. He's an absolute expert in numerical simulations, and he helped me so much during the pandemic. It was wonderful. We had Zoom meetings trying to debug a repo. If you have ever tried to debug a repo, you know that this is no small feat. I also want to acknowledge Luke Kelly, who is at Berkeley and who remains a very close collaborator of mine. Luke has been introducing me to the topic of massive black hole binaries and also introduced me to the nanograph collaboration that I also want to acknowledge. The nanograph collaboration is a wonderful collaboration of really, really amazing scientists and people, and I felt more than welcome at every meeting, and it's been wonderful to be part of it. The Hernquist group, okay, right. So again, I've been fortunate to be part of such a socially vibrant group that does amazing science. Here you can see us at our Friday wine meetings in the garden. The garden also has a patio where we do social events, which is really fun. We were also productive at times because the garden has a mouse problem. And one time we all got together and we set all these mouse traps. We never caught anything, but it was pretty productive. Try doing this after a glass of wine. It was hard. And I also want to point out Vadim, who looks at this glass of wine like I've never seen anyone look at a glass of wine before. So, yeah. Dr. Delgado, yeah. So Ana Maria has been raising the bar at our wine meetings by improving the quality control of the glasses. If you know Lars, you know that Lars provides excellent wine. And Ana Maria just realized we need to, raise the bar of the glasses. And, most of the time it wasn't up to standard. But I think we're getting better thanks to you. So thank you for that and many other things. I want to acknowledge many of my friends. My oldest friend, Victoria Shui, who is hopefully watching from Germany. Thank you. Oda Bolme in Norway. Sarah, and yay. Dr. Mike, Ralph, many people that I really appreciate and who have been making this journey so much more fun. Thank you also to my family. Some of you are here. Thank you very much for supporting me. And thank you also those who are watching from home. And finally, I want to thank Kuba, my husband, who has been a rock for me during this time. He is he's just as interested in mushrooms and gardening as me. He's been incredible helping with the garden. And I really think that our shared passion for the natural world has not only grounded me, but it's also made me a more creative scientist. So thank you. We've been on many adventures together, and I look forward to more to come.
Plenty of time for questions if anybody would like to ask Magda anything.
I can be loud. So first of all, Magda, thank you for a lovely talk, and thank you for, of course, your work at the garden. It's the best place at the CFA. Now the technical question. So you compute these time derivatives of these parameters of each binary, but my understanding is that in your simulations, the actual physical positions of the gravitators don't evolve. So is this done in post-processing? And
it's
then you
done.
apply that to the parameters in your 2D space and over time in some stepwise function, or how are you doing that?
Yeah, that's a great question. So we compute the gravitational force between the binary and all of the gas cells on the fly, actually about 100 times per orbit. And then we I can't say that word. We add up, the change in angular momentum and energy that the binary would experience were these forces applied to the actual binary orbit. And the reason that we do this is because we want the binary to get into a steady state, or the disk rather, to get into a steady state, so that we can compute the orbital evolution rates in a steady state system. If we let the binary evolve on the fly, things might actually be determined by the initial conditions, by the gas distribution that's initially there, and you might never actually get a proper steady state. So that's why we That's why we keep the orbit steady and we just compute the angular momentum and energy rate of change on the fly.
Daniel?
This movie sort of shows the effect I'm curious about. So there's this cavity and also this sort of episodic accretion onto the individual black holes. And I found myself wondering if this gets about the superheavy accretion rates.
Yeah, this is a really good question. So I think that much of this is likely limited by the sync radius that we choose. So the question I think that we have to ask is if we are at a total Eddington accretion rate and more of the accretion rate goes to the secondary, then yes, it should be a super Eddington accretion flow onto the secondary. But we don't include effects such as, again, like a smaller sync radius, which might change some of the sharing of gas between the two particles. We also don't include things like feedback, and I think that might be significant. I also have gripes about the viscosity models that we want to improve in future work, but I do think that super Eddington accretion could potentially happen onto the secondary in such an accretion flow. We just haven't included the necessary physics to verify that. Does that answer your question? Yeah.
Thank you. It was a great talk. So can you give me a sense of the timescale for the supermassive black hole models you talked about, of when the binary disk drives you? What's the timescale that you drive to that equilibrium eccentricity compared to the timescale of the gravitational radiation bringing infall? So where do those things meet?
Yeah,
It's not obvious to me.
that's a great question. So the timescale is a few mega years to get to the equilibrium eccentricity. And crucially, this phase of circumbinary disk-driven evolution is dominant prior to the gravitational wave-dominated regime. So I'm going to just briefly go back to a slide that's relevant for this. Right. So in this model, we are including gravitational radiation, and still the binaries find the equilibrium eccentricity because the disk at that point in the orbital evolution is just dominant over the gravitational wave radiation. If I let this run further, the binaries will decrease in eccentricity due to circularization, but this is already in the frequency range where LSST and nanograv see these binary systems. So we do see a remnant of this equilibrium eccentricity in populations that are in the window where we can probe them.
Any more questions? If not, let's thank Magda again.